So in my presentation, I'm going to be focusing a lot on the quantifying impacts, and then my colleague Eric here will have some really practical tips for then maximizing some of those benefits. But along the lines of quantifying impacts, we'll be presenting some work that was funded by the Water Research Foundation as part of the ongoing effort by many to more tangibly incorporate forestry and urban trees into stormwater management programs. Before I go too far, though, I would like to acknowledge my collaborators at Kansas State, as well as my green infrastructure colleagues and gurus in the Kansas City region, Tom Jacobs and Lisa Treese, as well as our research managers at the Water Research Foundation, Katie Lackey and Katie Henderson, who both funded this work, as well as they also convened an excellent advisory committee that provided valuable feedback along the way. So very thankful to the contributions of others. I'll also note that the full report, which has more information than I'm going to present here, of course, is available online, and that would be a resource provided to you through this webinar. As you can see from the title of the report, our work also included or did include reviewing available literature to quantify both stormwater quality and quantity contributions from urban trees, and then also looking to try to assess these within the broader context of life cycle costs and benefits, so getting some of the ecosystem services. I'm not going to focus on that piece so much, but really focus, you can kind of see the green arrow pointing to parts that are more associated with quantifying contributions of urban trees to regulating stormwater quantity and quality. And so I'll be speaking along those lines, and then some of the tools that we developed through this project are also available at this website if you have interest to follow up with it. So with that introduction, I first wanted to start with an overview of some of the dominant processes through which trees can regulate runoff. So there's many, so I'll just hit a few of the key ones. But anytime it rains, some of that rainfall is intercepted in the canopy and won't reach the ground. It will be evaporated back into the air. The portion that does fall through the canopy is known as through fall. Some will also reach the ground as stem flow, so that would be funneled to the base of the tree. And if there's pervious area, either at the base of the tree and or under the tree, then of course you can have infiltration. Some of the water that would then be stored in the soil can be taken up through the tree and transpired out through the leaves through the processes of transpiration as well as some evaporation there as well. And so of those, when we start thinking about connecting that to regulating stormwater, interception is hugely important because that's water that won't even reach the ground with the potential to become runoff. Stem flow, if we've done our duties and provided these trees with a good place to grow, stem flow can also be an opportunity to capture in the soils, whether they're engineered or as some street trees may be, or on a more natural soil, a place to store that or prevent runoff from occurring. Through fall, of course, may end up on impervious surfaces if our tree canopy is overhanging roadways or other paved surfaces. And so that can become a part of our runoff budget. But then transpiration important because then we're drying out the soils in between. So that gets on the processes that are really important from a water quality side. When we start thinking about from a water quantity side, from a water quality side, where we start in terms of thinking about how trees can impact that is through atmospheric deposition. So trees actually do a great job of trapping pollutants in the air and improving our air quality actually, but those pollutants do remain on the leaf canopy until they are washed through during rainfall events, and so they can actually end up in some of that through fall. If there's pervious surfaces again, though, we can retain those and recycle them and through various below-ground processes. Those can be taken up into the tree and assimilated, but then when those leaves fall, if you've got deciduous trees, we have litter fall, that can also, well, we need to consider that when we're thinking about stormwater quality. So these are the primary processes that I'll be talking about, some of the data sets where we try to quantify or look at how those, how we could predict those and then tie those back to stormwater management. The reality is, though, of course, there's many variables that control any of these processes, and there's interactions among these variables, and so ultimately it's a little complex. There have been some models. So, for example, if you're familiar with the iTree series, they have a very nice iTree hydro model that takes a more process-based look at trying to really quantify or nail down how those processes might be happening for a given tree system. However, some of those types of models are maybe not, maybe a little bit more difficult to implement in terms of, kind of our standard or traditional approaches in the stormwater planning or design phases, and maybe not something that on a day-to-day basis stormwater managers or designers would be able to incorporate. And so our goal through this project was to account for these really important, even if complex, role of trees in regulating runoff, but in the context of stormwater management. Through developing, our intent was to develop, I'll call them simple statistical models. And so to do this, we mined existing data from over 40 studies that have been conducted in urban settings to look at canopy interception, for example, or the amount of through-fall interception, and then even some of the water quality processes discussed earlier. We then developed some of these statistical tools, or basically some sets of equations where we could try to predict, for example, how much canopy capture or other hydrologic benefits you might have, and then be able to actually quantify or predict those processes. That worked, as you'll see as we go along, that worked, I think, relatively well for processes like through-fall and canopy interception, kind of okay for transpiration. And then on the water quality side, we didn't get, the data just weren't there to support models for that, but I think some really important insights came from that. And so that's what I'll be sharing with you for the remainder of my time. So in terms of we'll call them again, these simple models or equations that we developed through the synthesis of the literature, these were primarily focused on those processes of interception, through-fall, stem flow as well, and then transpiration. And so what we did is with that data set that we amassed from these urban tree studies, we pulled out or extracted all the variables that the study authors had provided related to anything about tree characteristics, how big the trees were, the species, their canopy structure, climate variables, rainfall size events, and threw those all into a statistical model or a regression model. And out of that, we looked to develop, so you can see in the orange box there, some predictive equations, right? So we said, okay, we might, as stormwater managers, we'd be interested in how much rainfall capture we can have. So thinking about interception plus stem flow. So how much can we capture and keep from becoming runoff versus how much might become through fall and be falling on our impervious surfaces if we've got those underlying our trees. And then how much can we expect to transpire, move back up into the atmosphere with these. And so our goal was, again, for these to be relatively simple, easy to implement, and with hopefully easily measurable or obtainable variables, so things like temperature, for example, or rainfall size. But the important caveat here is that any of these types of statistically based models are reflective of the data that were in our data set. And so while we scoured the literature for these studies, at the end of the day, this is still a growing area of research. And so maybe these equations could change through time as we get more information. However, I think the power of this type of approach is that we are able to move from an individual study to look across this synthesis of what's been identified so far, and to pull out some commonalities from that we could broadly apply. So that's a little bit on our approach. Before I go into the models themselves or some of the key takeaways on the water quality side, I just want to throw out some of the key takeaways that I hope you take from this, and we'll emphasize again at the end. But as I present on the precipitation partitioning, or that going from what's being captured in the canopy as interception versus what's becoming through fall, We found that the most influential predictors were tree phenology, or do you have an evergreen or deciduous tree during leaf-on versus leaf-off periods, as well as precipitation depth. And with those simple variables, we could explain quite a lot of the variability that we would see across all of those data sets combined when we threw them into our statistical model. That was good news. On the side of transpiration, we found that in terms of the tree characteristics, the type of wood, or really the way that water is transferred through various types of tree species was important, as well as various different climate variables, solar radiation, vapor pressure deficit mainly. But there was still a lot of unexplained variability. So our transpiration models are not as great, but do give some, I think, some interesting insights to the effect of different tree species that you might select in different stormwater management applications. And then in terms of the insights from the water quality side, we saw that trees do some great work below ground. However, when you start thinking about the litter fall, if that litter has a direct pathway to a storm drain, then litter management is essential. So I'll show you some really interesting nutrient leaching data here in just a moment. So let's get into some of these data sets and some of the models, and hopefully then some potential applications of those that might be of use to you. So on the rainfall capture side, so talking about interception there, the data strongly show that interception is a non-trivial process, whether you're looking at an annual or an event timescale. So on the annual basis, that would be the graph you see on your left. And just put some numbers up here to kind of give you relative amounts. These are on a log scale, by the way, so we had non-normal data, so had to adjust those for our statistical models. But just some points here to kind of give you some indication of magnitude. But on an annual time scale, for places that receive a relatively low amount of rainfall, so as little as 250 millimeters per year on the left side of that axis up to 2,000 millimeters per year, we see that on an annual basis, that capture can range from 25 to 45% for low rainfall areas or more arid climates, but even still as high as 15 to 25%. And that range is dependent, you can kind of see some separation on whether you had deciduous trees versus evergreen trees. So on an annual basis, tend to have a higher percent capture under evergreen trees. But I say non-trivial is, taking 15 to 25% off your annual rainfall, even at a relatively high rate, could be some savings in terms of runoff management. At the event time scale, for really small events, so say less than a millimeter, trees are pretty effective in fully capturing those nearly. Where stormwater managers are probably more interested is indicated by this blue arrow. So that corresponds to what we might call a water quality event, or around an inch or 25 millimeters. And even at that type of event, the data as we set them here show about a range of 15 to 25% of that event being captured in the canopy. So again, non-trivial there. On the event basis, just to kind of explain what these different lines are, deciduous trees during their leaf-on period and evergreen trees were essentially the same. You can see a little bit of separation there, but statistically they were no different. And then when deciduous trees do not have their leaves, they're not as effective in capturing rainfall. So we do see a little bit of a separation there, but still a non-trivial amount. So these slides show what those data sets look like and how those curves fit there. I think we can think about the context as being important here, again, whether we're overhanging impervious versus pervious surfaces. But we do have presented in some of the resources that will be shared with you the full out equations. If you were wanting to utilize these as a planning type of, planning scale to get an idea of how much capture you might have for your location over the course of a year, or over, say, an event, a water quality event, for example, along with some of the other details. So I won't dive into this table here, but just know that those that is out there for you to explore further if that's of interest. On the transpiration side of things, from a stormwater management, we're interested in this. because again, it's that opportunity to squeeze out our soil sponge and restore the capacity to store the next rainfall event. From the data standpoint, some of the variables that emerged as being very relevant here were the type of wood. So these box plots that you see here correspond to diffuse forest trees, so trees like maples, poplars, birch, for example, versus ring forest trees, which would include elms, ashes, locusts, oaks, those kinds of trees, but different in terms of how they process water, for sure. So that was an interesting, or a nice finding from this data set. And then these trees here, the last box plot there you see for tracheids, those would be coniferous types of trees. The primary climate variables driving transpiration, at least in terms of their influence in the observed in the data sets that we compiled, were largely driven by vapor pressure deficit and solar radiation. So important climate variables that are measured typically at weather stations, and so they could be thrown into equations such as this to get an idea of the amount of water that you could expect to be pumped out of the soil by these tree systems. As part of this work, we did also compile all this. So if you're like, I'm not really into putting these equations in on myself, but we did develop a spreadsheet tool where we can kind of, I have a screenshot here of it, but take characteristics of your site, so the annual precipitation or event precipitation, and then it already programmed into the spreadsheet are the equations to then predict the amount of rainfall capture you might have based on your mix of evergreen versus deciduous trees, as well as then how much transpiration you might have, and even the last tab, developing a little bit of a soil water budget with that, or a runoff budget with that. So again, those tools and references should be available to you, and I'd be happy to follow up if you have any questions about them. With my last few moments here, before I turn over to Eric, I wanted to discuss some of the insights we were able to glean about urban trees and stormwater quality. I feel like a lot of the discussions I've been in when we talk about stormwater management in trees, it's very positive when we think about these, potential to impact stormwater volume, but the quality side, can sometimes be a little bit of an elephant in the room, or at least something we're not as sure about. And so 3 kind of key components that we considered from the water quality side, we're thinking about what's coming in through fall. So from all of those air quality particulates that are deposited in our canopy, what washes through fall, what's going on below the ground, and then what's happening in terms of litter fall. There haven't been enough studies to really put this into the same regression type of model that we did for the water quantity processes. But again, I'll focus on some of the insights gained here. So we found trees, again, I think that the concentrations are in through fall are enriched relative to precipitation, and that just shows they're doing a good job of filtering out pollutants. If these, and so this shows you for both forms of nitrogen as well as phosphorus. And if those land on the grounds, below grounds, so you've got some infiltration capacity under your trees, and trees also do a great job of processing and recycling those nutrients in the through fall. So the set of box plots here are showing you some studies that were done comparing leaching of nitrogen forms below tree canopies versus turf grass. Not a lot of studies, so it's hard to be hard and fast on these insights, but in general, trees tend to have fewer nutrients leached into groundwater or other pathways out of your system, and same for phosphorus. So that's an important insight. Trees are doing some good work in supplementing what we might have from other vegetation in our system. The third insight I'll share before I pass over to Eric is from the litter management. This is where I think the rubber really hits the road in terms of thinking about the quality implications of our urban trees. So these graphs are just showing a scatter of points to show that the nutrient dynamics in the litter after it lands on the ground are pretty complex, but a very interesting finding that we saw consistently across studies is shown in this plot I just brought up here that shows the loss of phosphorus over a relatively short time. So within a few weeks, tree litter tends to lose a lot of its phosphorus, and that's leached as water would pass through those during runoff events. And others have found through their studies that that can elevate phosphorus in our runoff entering our streams. And so I think an important takeaway from that is that our landscape context matters. If we can complete the full cycle and infiltrate into the ground, a lot of those nutrients are going to be retained in our urban tree soil systems. But when we've got impervious surfaces underlying our trees, particularly those with direct hydraulic connections to our stormwater networks and water bodies after that, then litter management is just essential. But I think we still have a lot of benefit, as you can see from the hydrologic side of things, that certainly would warrant that level of effort. So I will leave with these key findings. Again, rainfall capture is non-trivial, an important thing to consider from a stormwater management context. But on the quality side, street sweeping is very important to manage phosphorus. And I didn't really touch on the aspect of the size of the trees, but you get more benefit from an individual tree the larger it is. And so, if you seriously are, trying to consider incorporating trees as part of a stormwater management program, then partnering with folks who know how to keep trees healthy and get them to reach maturity is very important. So that concludes my part of today's webinar, and I look forward to any questions that y'all may have.